60,000 megawatts. A river that drops 2 kilometers in 50, the deepest canyon on the face of the Earth. And someone looked at all of that and said, yes, welcome back to the channel. What you are about to see is not a typical construction story. This is, without exaggeration, one of the most extreme, most expensive, and most controversial engineering undertakings ever attempted by human civilization. This is the Lower Yarlung Tsangpo Hydropower project, a cascade of 5 hydropower stations being built inside the deepest canyon on the planet, in one of the most seismically violent regions on Earth, at the roof of the world, with an estimated price tag of approximately 1.2 trillion yuan. That is roughly $137 billion or more. Let that number sit for a moment. 137 billion. This is not just a dam. This is not just a power plant. This is a system of 5 separate hydropower stations arranged in a cascade along a stretch of river that drops nearly 2,000 meters in elevation, in just 50 kilometers. That kind of gradient does not exist anywhere else on the planet at this scale. That kind of energy potential has never been harnessed before. This is not an upgrade to something that already exists. This is the invention of a new category of infrastructure, one that, when completed, would generate approximately 300 billion kilowatt-hours of electricity per year. That is roughly 3 times the annual output of the Three Gorges Dam, the current largest hydropower station on Earth, with its 22.5 gigawatts of installed capacity. The Yarlung Tsangpo project is designed for 60 gigawatts, 3 times the power, in a place where most people would never dare to build a road, let alone the largest power plant in human history. So where exactly is this place? And why is it so difficult? Picture this. You're standing in southeastern Tibet. The air is thin. The oxygen level is roughly 40% lower than at sea level. The temperature swings from scorching daytime heat to sub-zero, cold overnight. The ground beneath your feet is unstable, fractured by millennia of tectonic collision between the Indian plate and the Eurasian plate. Now look up. On one side, Mount Namcha Barwa rises to 7,782 meters. On the other side, Gyala Peri, 7,294 meters. Between these two giants, the Yarlung Tsangpo River makes a sharp, dramatic U. Turn a feature geologists call the Great Bend. And as it bends, it plunges. It drops nearly 2,000 meters in just 50 kilometers, carving through rock, through time, through everything in its path. The result is the Yarlung Tsangpo Grand Canyon, approximately 504.6 kilometers long, with a maximum depth of roughly 6,009 meters. That makes it the deepest canyon on Earth, deeper than the Grand Canyon, deeper than the Kali Gandaki Gorge, deeper than anything you have ever seen in a photograph. And this is not just a deep canyon. This is a canyon that moves. The rock here is metamorphic, gneiss, schist, layers that were once buried deep inside the Earth's crust and pushed upward by the collision of continents. The canyon walls are steep, fractured, and prone to landslides. Rivers of glacial meltwater pour down the sides. The monsoon season brings torrential rain. Fog blankets the valleys for weeks at a time. Entire hillsides can collapse without warning. And beneath all of this fault lines, active, restless, unpredictable fault lines. In 1950, this very region was struck by one of the most powerful earthquakes ever recorded on land, the Assam-Tibet earthquake, magnitude 8.6. Think about that number, magnitude 8.6. That earthquake flattened villages. It triggered massive landslides that blocked rivers. It created natural dams that later burst, sending catastrophic flood waves downstream. Entire communities were buried. The landscape itself was reshaped, and this is the spot. This exact geological neighborhood, where China has decided to build the largest hydropower complex in the history of civilization. Earthquakes, landslides, glacial floods, extreme altitude, thin air, freezing temperatures, monsoon rains, fractured rock, no existing roads, no existing rail, no existing grid, no existing supply chain, and they decided to build 5 hydropower stations, connected in sequence, designed to capture the energy of a river that falls 2 kilometers in 50 and send that electricity thousands of kilometers east across the country through some of the most advanced power transmission infrastructure ever conceived. Before we continue, make sure to subscribe to the channel and hit the bell icon so you do not miss the next video. What if I told you that this project is not just about electricity? What if the real story is about water and who controls it? Stay with us until the end, because the geopolitical dimension of this project will change the way you think about rivers forever. Now, let us go back to the beginning. Before the machines, before the engineers, before any of this was possible. At first, there was only the canyon, only the river, only the wind howling between walls of rock 6,000 meters deep. No roads, no bridges, no settlements for hundreds of kilometers in every direction. No power lines, no cell towers, no hospitals, no fuel stations, just raw, untouched, magnificent, and terrifying geology. The Yarlung Tsangpo had been flowing through this canyon for millions of years, uninterrupted, undisturbed, carrying glacial melt from the Himalayas down through Tibet, around the Great Bend, and onward crossing into India. One river, 3 countries, 3 names, billions of people downstream who depend on it for drinking water, agriculture, fishing, transportation, and survival. The idea of harnessing the Great Bend's energy was not new. Chinese engineers and hydrologists had studied this section of the river for decades. They knew the numbers, they knew the gradient, they knew the volume. The Yarlung Tsangpo carries enormous quantities of water, glacial melt from the Himalayas, monsoon rain from the Indian Ocean, snowpack from the Tibetan Plateau. And at the Great Bend, all of that water is forced through a narrow, steep corridor where gravity does the rest. The potential energy locked in that 2,000-meter drop is staggering. It is quite literally the most energy-dense river section on the planet. But knowing the potential and actually building something here, those are 2 completely different problems. If you try to build a conventional dam across the canyon, the walls are too steep, the rock too fractured. A single massive dam would need foundations, anchored into geology that has been shattered by millions of years of tectonic violence. If you try to divert the river through a single tunnel, the distances are too great, the rock too unpredictable, the water pressure too extreme. If you try to build from the valley floor, you have no access, no roads, no staging areas, no flat ground for equipment, no way to bring in the thousands of tons of materials you need. If you try to build from the canyon rim, you are working at altitudes where construction equipment loses efficiency, where workers struggle to breathe, where weather can shut down operations for weeks at a time. Every conventional approach fails. Every standard engineering playbook falls apart against this landscape. So the solution was not simple. It was not a single tunnel. It was not a single power station. The solution was a cascade, a system of 5 separate hydropower stations, arranged in sequence along the river's descent, each one capturing a portion of the 2,000-meter drop. Each station positioned at a carefully calculated elevation, each one connected to the next by the river itself. The water passes through the first station, generates power, is released downstream, falls further, enters the second station, generates more power, is released again, falls further, enters the third, and so on. 5 stations, 5 bites at the same river, 5 chances to extract energy from the same water as it descends through the deepest canyon on Earth. This was not a compromise. This was the only architecture that could work. A single dam would require impossible foundations. A single tunnel would require impossible lengths, but a cascade distributes the engineering challenge across 5 separate, more manageable structures. Each dam can be smaller. Each tunnel can be shorter. Each foundation can be anchored into a specific, carefully studied section of rock. The total system achieves what no single structure could. And to make this cascade work, everything had to begin with the survey. The survey phase of the Yarlung Tsangpo project was not like any survey you have seen before. This was not a team with measuring tapes and clipboards walking across a construction site. This was an expedition into one of the most remote, most inaccessible, and most dangerous landscapes on the planet. Teams of geologists, hydrologists, seismologists, structural engineers, environmental scientists, and cartographers had to physically enter the canyon, some sections of which had never been mapped in detail. They used satellite imagery, aerial LIDAR, scanning drone-based photogrammetry, ground-penetrating radar, and seismic reflection surveys to build a three-dimensional picture of the canyon's geology. They needed to know the composition of every rock layer, the location of every fault line, the flow rate of the river at every point along the cascade, the sediment load, the flood history, the monsoon patterns, the glacial melt cycles, the landslide risk zones, the wind patterns, the temperature extremes, the snow accumulation, the ice formation. Every data point mattered. A single miscalculation in rock strength could mean a dam foundation failure. A single error in flood modeling could mean a catastrophic overtopping event. A single overlooked fault line could mean a reservoir-induced earthquake. The survey teams spent years in the field. Years, not months. They drilled test boreholes into the canyon walls to extract rock cores, cylinders of stone pulled from hundreds of meters below the surface, analyzed in laboratories for compressive strength, porosity, fracture density, and mineral composition. They installed seismic monitoring stations throughout the canyon to record micro-earthquakes, tiny tremors that reveal the behavior of the fault systems below. They deployed river gauging stations to measure the flow rate of the Yarlung Tsangpo at dozens of points along the cascade. Across every season, in every weather condition, they mapped the monsoon flood patterns going back decades, using satellite data, historical records, and sediment analysis. They did not just study the river, they studied the mountains above the river. They mapped the glaciers feeding the river, glaciers that are retreating due to climate change, glaciers whose meltwater could dramatically alter the river's flow in the coming decades. They mapped the slopes above each proposed dam site to identify landslide hazards, slopes that could collapse during an earthquake or a heavy rain event, sending millions of tons of rock and debris into a reservoir, potentially creating a wave that overtops the dam. Every slope mattered, every fracture mattered. Then came the access infrastructure. And this, in many ways, was a mega project within the mega project. You cannot build 5 hydropower stations in the deepest canyon on Earth if you cannot reach them. And reaching the construction sites along the lower Yarlung Tsangpo, the region around Midog County was until very recently one of the last counties in China without a year. Round road connection, the terrain is so extreme, deep valleys, sheer cliffs, dense subtropical forest at lower elevations, ice and snow at higher elevations, that building a single road requires tunnels, bridges, retaining walls, avalanche shelters, drainage systems. The construction of access roads to the dam sites meant carving through mountains, literally blasting tunnels through solid rock, building bridges across gorges hundreds of meters deep, constructing switchback roads along cliff faces where a single miscalculation means a vehicle drops into the abyss. Every road had to be designed not just for cars and trucks, but for the heaviest construction equipment on Earth. The massive crawlers, the heavy lift cranes, the concrete mixing plants, the turbine components, the transformer units, the steel reinforcement, the precast segments, the tunnel boring machine parts. Each piece of equipment had to be transported from manufacturing facilities in eastern China thousands of kilometers away along highways, through mountain passes, across rivers, and finally up narrow, newly built mountain roads to the construction sites deep inside the canyon. Imagine the scale of that logistics chain. A single large turbine runner can weigh hundreds of tons. A single transformer unit can weigh hundreds of tons. These are not items you can carry in a truck. They require specialized heavy-haul vehicles, custom-built trailers, reinforced road surfaces, and sometimes temporary bridges built solely to carry a single load across a single gorge. Bridges that are dismantled after the load passes. The logistics of simply getting materials to the site is an engineering feat that most construction projects never have to consider. And the access roads were just the beginning. The construction teams also needed worker housing, dining facilities, medical clinics, equipment maintenance, communication systems, helicopter landing pads, emergency evacuation routes, all built from scratch, at altitude, in a canyon, before a single cubic meter of concrete could be poured for the actual dams. Then came the river diversion. Before you can build a dam in a river, you have to move the river out of the way. This is one of the most critical and most dangerous phases of any hydropower construction project. The Yarlung Tsangpo is not a gentle stream. It is one of the highest volume rivers on the Tibetan Plateau, carrying enormous quantities of glacial meltwater, monsoon runoff, and sediment. During the monsoon season, the flow rate can surge dramatically. What was a manageable river in the dry season becomes a roaring, churning torrent of brown water, boulders, and debris. To build the foundation of a dam, you need a dry riverbed. And to get a dry riverbed, you need to redirect the entire river through a temporary diversion channel. Usually a tunnel blasted through the canyon wall alongside the dam site. This was not one diversion. This was 5 diversions, one for each station in the cascade. Each diversion tunnel had to be large enough to handle the full flow of the river during monsoon season. Each tunnel had to be lined with reinforced concrete to withstand the erosive force of sediment-laden water. Each tunnel had to be positioned at exactly the right elevation, too high, and the river backs up and floods the construction site, too low, and the tunnel cannot drain fast enough. Each tunnel entrance and exit had to be protected with massive cofferdams, temporary barriers built across the river upstream and downstream of the dam site, holding back the water while the permanent structure is built behind them. Building a cofferdam in the Yarlung Tsangpo is not like building a cofferdam in a calm river. The water here is cold. It is fast. It carries rocks the size of cars. The riverbed is uneven, strewn with boulders deposited by ancient glacial floods. The workers and machines that build these cofferdams operate in conditions that would shut down most construction sites in the world. Freezing spray, roaring current, unstable footing, altitude sickness, limited visibility from mist and fog. Every cofferdam had to hold. Every diversion tunnel had to function. Because if a cofferdam fails during construction, if the river breaks through while workers are in the foundation pit, the consequences are catastrophic. There is no margin for error at this stage. None. Once the river was diverted, once the construction teams had a dry section of riverbed to work with, the real excavation began. The foundation of a dam is everything. It does not matter how strong the dam itself is, if the rock beneath it cannot support the load. And in the Yarlung Tsangpo Canyon, the rock is complicated. It has been compressed, folded, fractured, and metamorphosed by millions of years of continental collision. It is not uniform. It is not predictable. What looks solid on the surface can be riddled with fractures, voids, and weak seams just meters below. The foundation engineers had to excavate down through layers of weathered rock, loose debris, and alluvial sediment until they reached what they call competent rock. Solid, intact, unfractured stone, capable of bearing the immense load of a dam and the water pressure behind it. At each of the 5 dam sites, this meant removing enormous volumes of material. Blasting, drilling, excavating, loading, hauling. Day after day, week after week, month after month. The excavated material, tens of thousands, hundreds of thousands of cubic meters of rock and soil, had to go somewhere. It could not simply be dumped into the river. It could not be left on the canyon floor, where it might obstruct water flow or create landslide hazards downstream. It had to be transported to designated spoil sites, carefully selected and engineered to ensure long-term stability. And as the excavation went deeper, a new challenge emerged Grand Walt. Water seeps through every fracture, every joint, every bedding plane in the rock. As the excavation pits deepened, water flooded in from all sides. Pumping systems had to run constantly, massive pumps pulling thousands of liters per minute out of the excavation pits, channeling the water into treatment systems before it could be released back into the environment. Without continuous pumping, the pits would flood within hours. Work would stop, schedules would slip, costs would climb. Every pump had to run. Every drain had to flow. Once the foundation excavation reached competent rock at each dam site, the next step was foundation treatment, a process of strengthening watertight base for the dam. This involved a technique called consolidation, grouting, drilling hundreds of boreholes into the rock below the dam footprint, and injecting a mixture of cement and water under pressure. The grout flows into fractures, fissures, and voids in the rock, filling them, hardening, and binding the rock mass together into a denser, stronger, more uniform structure. But consolidation grouting alone was not enough. The engineers also had to install a grout curtain, a deep, continuous wall of hardened grout injected into the rock below and around the dam, designed to block the passage of water underneath and around the structure. Without a grout curtain, the immense water pressure of a full reservoir would force water through the fractures in the rock, creating seepage paths that could erode the foundation from within, a phenomenon engineers call piping. Piping is silent. Piping is invisible. Piping is one of the leading causes of dam failure. Worldwide, the grout curtain is the defense against it. At each of the 5 dam sites, hundreds of grout holes were drilled. Each hole was drilled to a precise depth at a precise angle, following a precise pattern designed to create a continuous underground barrier. The grout was mixed on site to exact specifications. The ratio of cement to water, the viscosity, the injection pressure, all calibrated to the specific rock conditions at each location. Too much pressure, and you fracture the rock further. Too little, and the grout does not penetrate deep enough. The grouting teams worked methodically, hole by hole, row by row, curtain by curtain, sealing the mountain beneath each dam site against the enormous hydraulic forces that would press against it once the reservoirs filled. This was not glamorous work. This was not the kind of engineering that makes headlines. But without it, without every single grout hole, without every single liter of cement slurry injected into the fractured heart of the canyon, none of the dams above could stand. Without it, failure. With it, the foundation for the largest hydropower complex ever conceived. Then came the concrete, the skeleton. The substance that would turn a treated rock surface into the body of a dam. Pouring concrete inside the deepest canyon on Earth is not like pouring concrete on a flat construction site in Shanghai. Everything about the environment works against you. The altitude affects the curing chemistry at higher elevations. Lower atmospheric pressure changes how air bubbles behave inside the concrete mix. The canyon walls channel wind, cold, damp, unpredictable wind that accelerates evaporation from exposed concrete surfaces, causing premature drying and surface cracking. The humidity swings wildly between the dry winter months and the monsoon season, meaning the moisture content of the concrete has to be constantly adjusted. And the remoteness of the site means that every bag of cement, every ton of aggregate, every liter of mixing water, every chemical admixture has to be transported hundreds of kilometers along narrow mountain roads before it ever reaches the mixing plant at the dam site. This was not a single pour. This was not even 100 pours. Building the dam bodies across 5 cascade stations required hundreds of thousands of individual concrete placements, each one a carefully orchestrated operation involving batching, mixing, transporting, placing, vibrating, and curing. Each placement had to be planned to avoid cold joints, weak seams that form when fresh concrete is poured against a previously poured layer that has already begun to harden. Cold joints are planes of weakness in a dam body. They are where water finds its way in. They are where cracks begin. Every pour had to be timed so that the previous layer was still receptive, still warm, still workable, still capable of bonding with the new layer above it. The mixing plants at each dam site were themselves small industrial complexes. Cement silos, auggie-at stockpiles, gravel and sand, sourced from designated quarries in the surrounding mountains, crushed and screened to precise gradations. Fly ash storage, water tanks, chemical admixture, dosing systems, conveyor belts, cooling systems, because the chemical reaction that hardens concrete generates heat, and in a massive dam pour, that heat builds up inside the structure. If it builds too much, the interior of the dam expands while the exterior cools, and the differential creates internal stresses that crack the concrete from within. The mixing plants had to produce concrete with precisely controlled temperature, often using chilled water, ice flakes mixed into the aggregate, or liquid nitrogen injection to keep the placement temperature within a narrow window. Imagine a concrete mixing plant perched on a narrow ledge carved into the wall of the deepest canyon on Earth. Below, the diverted river roars through its temporary tunnel. Above, the canyon walls rise thousands of meters into mist and cloud. Helicopters shuttle supplies to areas the roads cannot reach. Cranes swing loads across gaps where a single dropped cable could mean disaster. And in the middle of all of this, the concrete keeps flowing. Bucket by bucket, layer by layer, meter by meter, the dam bodies grow. Each dam in the cascade was designed to the specific conditions of its site, the width of the canyon at that point, the rock quality on each abutment, the flow rate of the river, the volume of the reservoir behind it, the seismic loading it must withstand. No two dams in the cascade are identical. Each one is a custom structure, tailored to the geometry and geology of its location. The engineering teams used computational models, finite element analysis, three-dimensional stress modeling, seismic simulation, to test each design against hundreds of failure scenarios. What happens if a landslide dumps 1 million cubic meters of debris into the reservoir? What happens if the monsoon brings a once-in-a-thousand-year flood? Every scenario was modeled. Every weakness was identified. Every design was iterated until the safety margins met the required standards. Then came the spillways. A dam without a spillway is a dam waiting to fail. Spillways are the safety valves of hydropower infrastructure. They allow excess water to pass over, through, or around the dam in a controlled manner during flood events. Without them, a flood can overtop the dam, and overtopping is one of the most catastrophic failure modes in dam engineering. The water cascading over the top erodes the downstream face of the dam. The erosion accelerates, and within hours, the entire structure can be breached. At each of the 5 stations in the Yarlung Tsangpo Cascade, the spillway design had to account for the extreme flood potential of the river. This is a river fed by Himalayan glaciers, monsoon rains, and snowmelt from the Tibetan Plateau. Simultaneously, during a major monsoon event, the flow can increase many times over its dry season baseline. The spillways had to be sized not just for the average flood, but for the maximum credible flood, the worst-case scenario that probabilistic analysis says could happen once in 10,000 years. Because in dam engineering, you do not design for probability. You design for consequence, and the consequence of a dam failure in this canyon, with 4 more dams downstream in the same cascade, would be unthinkable. The spillway structures required their own massive concrete works, chute channels, stilling basins, flip buckets, energy dissipation structures, all designed to slow and calm the water before it re-enters the river downstream. The forces involved are almost incomprehensible. A high-velocity spillway discharge can generate forces equivalent to thousands of tons per square meter. The concrete lining of the chute has to withstand not just the water, but the sediment and rocks carried by the water, an abrasive grinding flow that can destroy ordinary concrete in a single flood season. Special high-strength, abrasion-resistant concrete was developed for these surfaces, reinforced with steel fiber and coated with apoxy in critical zones. Every spillway gate had to open. Every energy dissipator had to function, because the day they are needed is the day there is no second chance. Then came the powerhouse caverns. In most hydropower projects, the turbines and generators are housed inside the dam structure itself or in a building adjacent to it. But in the Yarlung Tsangpo Canyon, the surface conditions are too extreme, the canyon walls too steep, the landslide risk too high for surface-mounted powerhouses. The only solution, was to go underground. At each of the 5 stations, the construction teams had to excavate enormous underground caverns inside the mountain caverns, large enough to house the turbines, the generators, the transformers, the control rooms, the cooling systems, the ventilation systems, the access tunnels, the cable galleries, and the maintenance bays. These are not small rooms. A single powerhouse cavern for a major hydropower station can be hundreds of meters long, tens of meters wide, and tens of meters tall. A cathedral carved out of solid rock, deep inside a mountain, with no natural light, no natural ventilation, and no margin for structural failure. The excavation of these caverns was a masterpiece of underground engineering. It began with pilot tunnels, small-diameter tunnels driven into the mountain to access the location of the future cavern and to provide geological. Core samples were taken. Rock quality was assessed. Stress measurements. The excavation proceeded in stages, top, down, layer by layer. The roof of the cavern was excavated first and immediately reinforced with rock bolts, steel mesh, shotcrete, and in some sections, pre-stressed cable anchors driven deep into the surrounding rock. Then the next layer was excavated and reinforced. Then the next and the next. Each layer brought new challenges, changing rock quality, water inflows, stress redistributions, temperature changes. The excavation teams worked around the clock, drilling, blasting, mucking out the broken rock, installing support, monitoring instruments, adjusting their approach based on real-time data from sensors. Imagine standing inside one of these caverns during construction. The air is thick with dust and diesel fumes from the excavation equipment. The noise is deafening. Drilling rigs, ventilation fans, pumps, loaders, the constant crack and rumble of rock being broken. The temperature is stable deep underground. The rock maintains a constant temperature, but the humidity is high, and condensation drips from the ceiling. Workers wear headlamps. Communication is by radio. The only way in or out is through tunnels that can be hundreds of meters long. And all around you, the mountain is pressing inward, held at bay by rock bolts and shotcrete, and the precise calculations of engineers who designed this space to exist in a place that was never meant to be hollow. Once the caverns were excavated and stabilized, the installation of the mechanical and electrical equipment began, and this is where the project transforms from a story of geology and concrete into a story of precision engineering. Then came the penstocks. The penstocks are the arteries of a hydropower station. They are the large diameter pipes, or in this case steel-lined tunnels that carry water from the reservoir above, down through the mountain, to the turbines inside the powerhouse cavern below. The water enters the penstock at high elevation. It accelerates as it descends, converting potential energy, the energy of height, into kinetic energy. The energy of motion. By the time it reaches the turbine at the bottom, it is moving with enormous velocity and enormous pressure. At the Yarlung Tsangpo Cascade, the penstocks had to handle water pressures that are among the highest in any hydropower installation on Earth. The elevation drops between each reservoir and its corresponding powerhouse are extreme. That is the whole point of the project. That extreme drop means extreme pressure, and extreme pressure means the penstock lining the steel shell that contains the water has to be extraordinarily strong. The steel plates used for penstock linings at this project were fabricated to exacting specifications: precise thickness, precise alloy composition, precise heat treatment to achieve the required tensile strength and ductility. Each plate was rolled into a curved section, welded to the adjacent plates, X-rayed to verify weld integrity, pressure tested, and then installed section by section inside the penstock tunnel. The penstock tunnels themselves were drilled through the mountain using a combination of drill and blast methods, and in some sections, tunnel boring machines. The route of each penstock was determined by geological survey, avoiding fault zones, avoiding water, bearing fractures, following the strongest, most stable rock paths through the mountain. The tunnels were lined first with concrete, then with the fabricated steel shell. Then the annular gap between the steel and the concrete was grouted to ensure full contact and load transfer. Every weld mattered. Every bolt mattered. Because a penstock failure under full pressure is one of the most violent events in engineering. The water, compressed to enormous pressures, erupts through the breach with the force of an explosion. It can destroy the powerhouse, flood the underground caverns, and kill anyone inside. Penstock integrity is not a design preference. It is a survival requirement. Then came the turbines. The turbines are the heart of the entire system. Everything else, the dams, the reservoirs, the diversion tunnels, the foundations, the cofferdams, the penstocks, the caverns, all of it exists to serve one purpose: to deliver water to the turbines at the right pressure and the right flow rate, so that the turbines can spin and convert the energy of moving water into rotational mechanical energy. The turbines specified for the Yarlung Tsangpo Cascade are among the most powerful hydraulic turbines ever manufactured. Given the extreme head, the elevation difference between reservoir and turbine, the turbines are designed to operate efficiently. Each turbine runner, the rotating component that the water strikes, was manufactured to tolerances measured in fractions of a millimeter. The runner is a massive structure, a single piece of cast and machined steel, shaped with curved blades designed by computational fluid dynamics to extract the maximum energy from the water with the minimum turbulence and cavitation. Cavitation, the formation and violent collapse of vapor bubbles in high-velocity water, is the enemy of every hydraulic turbine. It erodes metal surfaces, creates vibrations, reduces efficiency, and can destroy a runner in a matter of months if left unchecked. The blade geometry, the surface finish, the operating parameters. The runners for this project were tested in scale, model test rigs before full-scale manufacturing began, and then tested again after installation, under real operating conditions, with sensors measuring vibration, pressure, temperature, and cavitation noise at dozens of points across the runner's surface. Each turbine drives a generator, a massive electromagnetic machine that converts the rotational energy of the turbine shaft into electrical energy. The generators for this project are synchronous machines, each weighing thousands of tons, with rotors spinning inside stators, wound with kilometers of copper conductor. The rotor turns. The magnetic field rotates. Electricity flows. This is the fundamental principle that Michael Faraday demonstrated in 1831, electromagnetic induction, scaled up to a level he could never have imagined. The generator stators were assembled inside the powerhouse caverns, piece by piece, coil by coil, wedge by wedge. The rotors were lowered into position by overhead cranes, installed on rails bolted to the cavern ceiling, cranes that themselves had to be assembled inside the cavern, since they were too large to be brought in whole through the access tunnels. The alignment of the rotor within the stator had to be precise to within fractions of a millimeter across a machine that spans meters in every direction. A misalignment of even a small fraction would cause vibration, heat, wear, and eventually, failure. Every coil had to be wound, every connection had to be torqued, every insulation layer had to be tested, every cooling circuit had to be sealed, every bearing had to be shimmed, every sensor had to be calibrated. Then came the transformers. The electricity generated by each turbine generator unit is produced at a specific voltage, a voltage amputated for the generator design, typically in the range of tens of kilovolts. But this voltage is far too low for efficient long-distance transmission. The power from the Yarlung Tsangpo is intended to travel thousands of kilometers from the remote canyons of southeastern and southern China. Over those distances, transmission losses would be enormous at generator voltage. The solution is to step up the voltage, to transform it to ultra-high levels using massive power transformers, and then transmit it via ultra-high voltage direct current lines that minimize losses over extreme distances. The transformers installed at each powerhouse are among the largest and heaviest individual components in the entire project. A single large power transformer can weigh several hundred tons. It is filled with thousands of liters of insulating oil. It contains windings made of specially processed copper or aluminum conductor, insulated with layers of oil-impregnated paper, wound around a core of grainy-oriented silicon steel laminations. The precision required in transformer manufacturing is extraordinary. The insulation must withstand voltage. Stress is measured in millions of volts per meter. And a single defect, a single void in the paper insulation, a single particle of contamination in the oil can cause a partial discharge that eventually leads to catastrophic failure. Transporting these transformers from the factory to the powerhouse cavern deep inside the canyon was an engineering challenge in itself. Each unit had to travel by heavy haul vehicle along mountain roads with tight switchbacks, steep grades, and weight limits. Some routes required road reinforcement, adding layers of compacted gravel, reinforcing bridge decks. In some cases, transformers were partially disassembled for transport and reassembled on site, a process requiring clean room conditions inside a dusty underground cavern. Once installed, each transformer was filled with oil, vacuum sealed, and subjected to a series of high-voltage tests, impulse tests, simulating lightning strikes, induced voltage tests, simulating system overvoltages, and heat-run tests, simulating full load operation for extended periods. Only after passing every test was a transformer cleared for connection to the grid. Then came the transmission lines. And this is where the project extends far beyond the canyon. The electricity generated at the Yarlung Tsangpo Cascade is useless if it stays in Tibet. The demand is thousands of kilometers away, in Guangdong, in the Greater Bay Area, in the industrial heartland of eastern China. Getting it there requires one of the most advanced power transmission systems ever built: ultra-high voltage, direct current transmission, or UHVDC. UHVDC is the only technology capable of transmitting massive amounts of electrical power over thousands of kilometers, with acceptable losses. Traditional alternating current transmission loses too much energy over such distances. Direct current at ultra-high voltage, hundreds of thousands of volts, even exceeding 1,000,000 volts, can carry gigawatts of power across entire countries with losses of just a few percent. But building a UHVDC line is not like stringing ordinary power cables between wooden poles. The voltages involved are so extreme that the insulation requirements, the tower designs, the conductor specifications, and the converter station equipment are all at the outer edge of electrical engineering capability. The Zhejiang to Guangdong UHVDC transmission line, one of the key lines being built to carry power from this project, spans approximately 2,681 kilometers. Construction of its Tibet section began in April 2026. This line will carry power from the Tibetan Plateau through Yunnan Province and the Guangxi Zhuang Autonomous Region to the Guangdong, Hong Kong, Macau, Greater Bay Area. It is designed for a transmission capacity of 10 gigawatts, enough to power tens of millions of homes. Building this line means erecting thousands of transmission towers across some of the most difficult terrain in China, the Tibetan Plateau at altitudes exceeding 4,000 meters, then down through the mountains and valleys of Yunnan, across rivers, over gorges, through forests and farmland to the coast. Each tower had to be designed for its specific location, its altitude, its wind loading, its ice loading, its seismic exposure. Each conductor span had to be calculated for sag, tension, and clearance. Each insulator string had to be rated for the specific pollution and humidity conditions of its location. The construction crews worked at altitude, in remote locations, often accessible only by helicopter or mule track, erecting towers that weigh tens of tons and stand tens of meters tall. Every tower had to stand, every conductor had to hold. Every insulator had to isolate, but the transmission towers and the conductors are only half the story. At each end of the UHVDC line, at the sending end in Tibet and at the receiving end in Guangdong, a converter station had to be built. These are the most complex electrical installations in the entire project. A UHVDC converter station is the place where alternating current from the generators is converted into direct current for transmission, and then thousands of kilometers away, converted back into alternating current for distribution to the grid. The technology inside these stations is extraordinary. Massive valve halls, cathedral-sized rooms, house stacks of dither-shaded centifor, Chencherv modules. Each one, a precisely controlled electronic switch that chops the alternating current into direct current at hundreds of thousands of volts. The heat generated by these switching operations is enormous, requiring dedicated cooling systems, deionized water circuits, heat exchangers. The control systems that govern the converter stations are among the most sophisticated real-time computing systems in the power industry, monitoring voltage, current, frequency, harmonic distortion, and dozens of other parameters thousands of times per second, adjusting the firing angles of the thyristors in real time to maintain stable power flow across the entire 2,681-kilometer line. A failure in a converter station does not just affect a single city block, it can black out an entire region. The redundancy built into these systems, backup thyristor modules, backup cooling circuits, backup control processors, backup communication links, backup power supplies, reflects the criticality of the infrastructure they support. Every valve had to fire, every cooling line had to circulate, every control algorithm had to execute. Then came the control and monitoring systems for the dams themselves. A cascade of 5 hydropower stations operating in sequence on the same river is not 5 independent projects. It is one integrated system. The water released from the first station flows into the reservoir of the second. The water released from the second flows into the third. A change in operations at any one station, opening a spillway gate, adjusting a turbine output, lowering a reservoir level, affects every station downstream. The control system that manages this cascade has to coordinate all 5 stations simultaneously, in real time, accounting for travel time of water between stations, inflow from tributaries, equipment maintenance schedules. This was not a simple automation task. This was the creation of one of the most complex real-time control systems in the history of hydropower engineering. Thousands of sensors, pressure transducers, flow meters, level gauges, seismographs, inclinometers, piezometers, thermocouple strain gauges, vibration sensors. Water quality monitors feed data continuously to a central control facility. Fiber optic communication networks link all 5 stations to the control center. Redundant satellite links provide backup communication in case the fiber is damaged by a landslide or earthquake. The control software runs on fault-tolerant computer systems with automatic failover. If one processor fails, another takes over cane. Without a single lost data point, the operators in the control room see everything: the water level in every reservoir, the flow rate through every turbine, the power output of every generator, the temperature of every bearing, the vibration signature of every rotating machine, the position of every gate, the status of every valve, the voltage at every bus bar, the load on every transmission line. They see the weather forecast. They see the seismic monitoring data. They see the glacial melt projections. They see the downstream river levels in India. Every sensor had to report. Every signal had to arrive. Every decision had to be made in time. Then came the reservoir, filling the moment when theory becomes reality. Filling a reservoir behind a newly constructed dam is one of the most critical and most carefully monitored events in hydropower engineering. The dam has been built. The foundation has been treated. The grout curtain has been installed. The spillways have been tested. The monitoring instruments have been calibrated. But until the reservoir fills, until the full hydraulic pressure of millions of cubic meters of water presses against the dam face and pushes down on the foundation and seeps into every fracture and joint in the surrounding rock. Until that moment, the dam has never truly been tested. The filling process is slow and deliberate. The reservoir is filled in stages, raising the water level by a few meters, then pausing for days or weeks to monitor the dam. Response: the instruments speak. The piezometers report the water pressure inside the dam body and inside the foundation rock. The seepage measurement weirs report the volume of water passing through and under the dam. The inclinometers report any tilting or displacement of the dam crest. The strain gauges report the stress distribution within the concrete. The seismographs report any micro earthquakes triggered by the weight of the new reservoir pressing down on the Earth's crust. A phenomenon called reservoir-induced seismicity. At each stage, the data is compared to the predictions of the engineering models. Does the dam deflect the way the models predicted? Does the seepage match the expected values? Is there any anomalous behavior, unexpected displacement, unexpected seepage, unexpected seismicity? If the data matches the models, the filling continues. If it does not, if something unexpected appears, the filling stops. The engineers investigate. They recalculate. They may even lower the water level to relieve pressure while they diagnose the issue. There is no rushing this process. A dam failure during first filling with a full construction workforce still on site, with downstream populations unaware, with emergency systems not yet fully tested, would be a disaster beyond measure. And this process happens not once, but 5 times. One for each dam in the cascade, each filling watched, measured, analyzed, and confirmed before the next dam downstream begins its own filling sequence. The cascade fills from the top down, the uppermost reservoir first, then the second, then the third, then the fourth, then the fifth. Each filling changes the hydrology of the river downstream. affecting the conditions at the next dam site. The entire sequence is choreographed like a symphony, every movement planned, every transition timed, every instrument monitored. Then came the commissioning of the generating units, the moment when water first hits the turbine runners and the generators spin to life. The first rotation, the first megawatt, the first electrons flowing from the deepest canyon on Earth, through the mountain, through the transformer, through the converter station, through 2681 kilometers of ultra-high voltage cable to a light switch in Guangdong. That moment, when a glacier-fed river in Tibet illuminates a factory floor thousands of kilometers away, is the culmination of every survey, every borehole, every blast, every concrete pour, every weld, every coil, every bolt, every line of control code that came before it. But commissioning is not the end. It is the beginning of a new phase, verification under load. Each generating unit had to be tested at partial load, then at full load, then at overload conditions. The vibration signatures were recorded and compared against acceptable thresholds. The bearing temperatures were monitored for anomalies. A bearing running even a few degrees hotter than expected can indicate misalignment, lubrication failure, or a manutation over time. The generator output was synchronized with the grid, a process that requires matching the voltage, frequency, and phase angle of the generator precisely to the existing grid signal. A synchronization error, even a fraction of a second off, can send a destructive surge through the generator windings and trip protective relays across the network. Then came the emergency shutdown drills. What happens when a turbine trips at full load? The water hammer, the pressure surge caused by suddenly stopping the flow in a penstock, can generate forces strong enough to rupture the steel lining. If the pressure relief systems do not respond in milliseconds, each station's pressure relief valves, bypass valves, and surge tanks were tested under simulated emergency conditions, again and again until the response times met the design specifications. The structural health monitoring systems were activated permanently. From this point forward, the dams, the caverns, the penstocks, the slopes above the reservoirs, and the transmission infrastructure would be monitored continuously, around the clock, every day of every year, for the entire operational life of the project. Accelerometers embedded in the dam bodies would detect seismic activity. Fiber optic strain, sensors running through the concrete would detect micro-deformations invisible to the human eye. Satellite-based synthetic aperture radar would track millimeter-scale ground movement on the slopes surrounding the reservoirs. Off-Diado weather stations would feed real-time precipitation data. This was not a project that would be built and forgotten. This was a project that would be watched forever. China had built on this river before. The Zhangmu Hydropower Station, 510 megawatts, operational since 2015, was the first large-scale dam on the main stream of the Yarlung Tsangpo. Zhangmu was the proof of concept, the test case. It demonstrated that construction was physically possible on this river, that the geology could be managed, that the logistics could be solved. But Zhangmu was a single station in a comparatively accessible section of the river, with a fraction of the capacity now being attempted. The lower Yarlung Tsangpo project is not Zhangmu scaled up. It is Zhangmu reimagined, multiplied by 5, pushed deeper into the canyon, driven to elevations and pressures that Zhangmu never approached. Every lesson learned at Zhangmu informed the design of the cascade. Every mistake discovered at Zhangmu was corrected before it could be repeated. But most people will never see any of that. Most people will only see the electricity. They will flip a switch, a light will turn on, a factory will hum, an air conditioner will cool a room in Shenzhen, and they will not think about where that power came from. They will not think about the canyon. They will not think about the river. They do not see the grout curtain, that invisible wall of hardened cement injected hundreds of meters into fractured rock, silently holding back the pressure of an entire reservoir. They do not see the penstocks, those steel-lined tunnels buried inside the mountain, carrying water at pressures that would crush a submarine. Day and night, year after year, without a single leak. They do not see the turbine runners spinning at hundreds of revolutions per minute inside caverns carved from solid rock, deep beneath mountains that have stood for 50 million years. They do not see the powerhouse caverns themselves, underground cathedrals of engineering, lit by artificial light, ventilated by fans, where workers walk corridors that exist inside the heart of a mountain that was never meant to be hollow. They do not see the cofferdam builders, the crews who stood in freezing, roaring water to stack rocks and drive sheet piles into an unstable riverbed, holding back a river so that others could pour concrete behind them. They do not see the surveyors, the men and women who spent years in the canyon, mapping every fault line, every fracture, every slope, every glacial stream, building a picture of the invisible geology. They do not see the road builders, the crews who blasted tunnels and carved switchbacks into cliff faces to create paths for machines that weigh hundreds of tons along roads where a single mistake means a fall of 1,000 meters. They do not see the transmission tower crews, workers who climb steel structures at altitudes above 4,000 meters in wind and ice and thin air to bolt conductors. They do not see the environmental monitoring teams, the biologists, the hydrologists, the ecologists who track sediment loads, fish migration patterns, water temperatures, and dissolved oxygen levels downstream, trying to measure the immeasurable, the ecological cost of turning a wild river into a managed one. They do not see the night shifts, the workers who pour concrete at 2 in the morning because the curing conditions are better when the air is cool, the control room operators who watch screens through the darkest hours, alone with the hum of servers and the glow of data, the only human presence in a cavern deep inside a mountain, listening to a river through instruments. They do not see the human cost, the years away from families, the altitude sickness, the isolation of working in one of the most remote places on Earth, where the nearest city is a day's drive away and the nearest hospital is even farther. The physical toll of high-altitude manual labor, headaches, fatigue, shortness of breath, sleepless nights, borne quietly by the people who build the things the rest of the world takes for granted. They do not see any of it, and that is exactly the point. The greatest engineering achievements are the ones that disappear, the ones that become invisible, the ones that integrate so completely into the fabric of daily life that no one stops to wonder how they got there. But there is something else that most people do not see, something that extends far beyond engineering, something that makes this project different from every other dam, every other power station, every other mega project on Earth. The Yarlung Tsangpo does not belong to China alone. This river, the river that is now being dammed, diverted, and harnessed inside the deepest canyon on the planet, does not stop at the Chinese border. It flows south. It crosses into India, where it becomes the Brahmaputra, one of the great rivers of the subcontinent, the lifeblood of Assam, the artery of northeastern India, a river that sustains tens of millions of farmers, fishermen, and families across one of the most densely populated floodplains on Earth. And then it flows into Bangladesh, where it becomes the Jamuna, merging with the Ganges and the Meghna before emptying into the Bay of Bengal, nourishing the delta that feeds a nation of over 170 million people. 3 countries, 1 river, billions of lives. The Brahmaputra is not just a water source, it is a sediment source. Every year, the river carries millions of tons of fine silt from the eroding Himalayas downstream, depositing it across the floodplains of Assam and the delta of Bangladesh. This sediment is what makes the soil fertile. It is what rebuilds the land that monsoon floods wash away. Trap that sediment behind a series of dams, and the floodplains starve. The soil loses its richness. The delta erodes faster than it rebuilds. The agricultural foundation of 2 nations begins to crumble slowly, invisibly, irreversibly. India and Bangladesh have watched this project with growing alarm. The concerns are not abstract, they are existential. If China controls the flow of the Yarlung Tsangpo, if it can store water during the dry season and release it during the monsoon, or withhold it entirely, then China holds a kind of power that no military can match. The power to flood, the power to drought, the power to reshape the agricultural calendar of an entire subcontinent. India calls it a strategic threat. Some analysts have called it a potential water bomb. India's response has been to accelerate its own counter. Project the Siang Upper Multipurpose Project, an 11,000 megawatt dam in Arunachal Pradesh, designed to serve as a strategic water storage facility that could mitigate sudden changes in flow caused by upstream operations in China. But this counter dam faces its own opposition from indigenous Adi communities whose ancestral lands would be flooded, from environmentalists who warn of irreversible ecological damage, from geologists who point out that the site is just as seismically active as the Chinese one, and so the river becomes a fault line of a different kind. Not geological, geopolitical, a fault line between nations, between development philosophies, between the human desire to harness nature and the natural limits of what can be controlled. China has stated that the project is designed for clean energy and will not harm downstream interests, but there is no comprehensive water sharing agreement between China, India, and Bangladesh. There is no independent monitoring. There is an expert-level mechanism, a diplomatic dialogue. But diplomacy is not infrastructure. Diplomacy can be paused. Infeeder cannot. Once the dams are built, once the reservoirs are filled, the physics of the situation changes permanently, and someone controls those gates. This is not speculation. This is hydraulics. This is geography. This is the reality of building the world's largest hydropower complex. On a transboundary river in one of the most geopolitically sensitive regions on Earth. And yet, and this is the paradox that sits at the center of this story, the project also represents something extraordinary, something undeniably magnificent. 60 gigawatts of clean energy, 300 billion kilowatt-hours per year, enough electricity to power entire provinces, enough to replace hundreds of coal-fired power plants, enough to materially accelerate the decarbonization of the world's largest energy system. The Yarlung Tsangpo project, if completed as designed, would be the single largest source of renewable energy on the planet. Not solar, not wind, not nuclear. Hydro. The oldest form of power generation, scaled to a level that the pioneers of hydroelectricity could not have conceived, and it is being built in a place that said no. A place that pushed back, a place that shook, fractured, flooded, froze, and isolated itself from human reach for millions of years. And still, the engineers came, the surveyors came, the blasters came, the concrete crews came, the turbine installers came, the cable pullers came, the control system programmers came. They came with their instruments and their models and their steel and their cement and their stubborn, relentless conviction that the canyon could be made to yield. Whether it should have been, that is a question for history to answer. But whether it could have been, that question is being answered right now, in concrete, in steel, in grout, in copper, in growls, in the roar of water hitting a turbine runner for the first time, deep inside a mountain, in the deepest canyon on Earth. There's a line that separates ambition from arrogance, and the Yarlung Tsangpo project walks that line every single day. Some will call this the greatest engineering achievement of the 21st century. A monument to human capability, a proof that there is no landscape too extreme, no challenge too great, no river too powerful for the determined application of science, labor, and will. Others will call it a cautionary tale, a reminder that the power to build is not the same as the wisdom to build, that a river shared by 3 nations cannot be claimed by one, that the deepest canyon on Earth was deep for a reason. And perhaps both are right. Perhaps this project is both a marvel and a warning, a triumph of engineering and a test of diplomacy, a source of clean energy and a source of geopolitical attention, a story of what humans can do and a question about what humans should do. One thing is certain, nothing like this has ever been built before, and whatever happens next, whether the turbines spin for a century or the geopolitics unravel within a decade, the story of the Yarlung Tsangpo will be studied, debated, and remembered for generations. Because it is not just a dam. It is not just a power station. It is a statement. A statement about what one civilization was willing to attempt, at the edge of what is physically possible, in a canyon that the Earth itself spent millions of years trying to make unreachable. 60,000 megawatts, a river that drops 2 kilometers in 50, the deepest canyon on the face of the Earth. And someone said yes. If you enjoyed this video, please subscribe to the channel. Hit the bell icon so you never miss a new release. Leave a comment below. I want to hear your thoughts. Should the world's largest dam be built in an earthquake zone? Is clean energy worth the geopolitical risk? And what happens to the people downstream? Thank you for watching. I will see you in the next one.